We live. I believe we are. Alright, this is going to be the very last lesson of the topic, so that's a little bit exciting. But I did say I was going to post a summary of the parabola, and I'll do that next lesson. But for now, this is the last content lesson, and it's kind of something we've already done before. It's just, I don't even remember back when we did equations. We solved a pair of simultaneous equations. So it might have been like, solve these equations, and then it might have given you two things like this. And then there was a bunch of different ways of doing that. There was elimination and substitution, and some people were using matrices and stuff. But elimination and substitution were the two that I taught you. And then I was like, okay, we'll write these, and then maybe call that 1 and call that 2, and then do 1 minus 2, and then stuff like that. And then you would have ended up with a solution, and then you would have been like, well, what is that solution? And I probably didn't tell you because we didn't really, I guess, get that far. We haven't graphed as much, and the whole last term we've been graphing things. So now it kind of makes sense to start talking about graphing things. So whenever you solve a pair of simultaneous equations, what you're actually doing is you're drawing two graphs and finding where they cross each other. So for instance, I've got this line, I've got this parabola. Let's suppose it looks like this and like that. You can see they cross each other there and there. So if I use algebra to solve that and that simultaneously, I should end up with two solutions, and my two solutions are going to be these two x and y coordinates. So that's what we were doing ages ago when we were doing simultaneous equations. We might have only been looking at lines, so we might have just been looking at one line and two line and being like, okay, that's where they cross. So I have an x and a y and that's it. But now we can recognize that since we can graph so many different things, we should be able to find more than one solution. And you can imagine that when we start graphing like things that look like this and then putting a line through it, you can see that there's many solutions, and that's kind of where we're building towards in terms of advanced. In terms of standard, generally if you're asked to find the points of intersection, it's going to be either given to you or you'll be given a really, really nice graph, and you probably won't have to do it algebraically. Yeah, but for us, as a kind of good practice to be able to graph these things and think about where they cross. So there's a couple of ways of doing this, but I guess, well, there's two really distinct ways. One would be to draw them and figure out where they are. But obviously, that's not going to be exact. But at the same time, if I were to do it like a really quick sketch of these two things, I can see kind of where they're going to be, and then I can use algebra to actually solve them and verify that where they were on my graphs is consistent. So what I mean by that is, let's suppose I drew those two things again. You can see that this one has negative x and y coordinates, and this one has positive x and y coordinates. So you'd suspect that your solutions are going to look like that. I don't know if that's actually what these graphs look like, but what I'm saying is you can quickly draw things like this and verify whether your answers make sense. So that's the whole point of the graphing topic, I think, is so that we can quickly draw things, which I feel like we should be able to quickly draw some of these. Maybe not this parabola because it's not really nice, but we can do the rest of them. So I normally start with a quick sketch. So I'll, I guess, look at it geometrically. So geometrically, and then I'll start looking at what it looks like algebraically. Okay, so for you, when you find a point of an intersection, you're just going to solve these algebraically, and you're going to end up with a point or 2 points or whatever. But if you want to check your answer, this is where drawing it comes in handy. So I'm going to draw them first so that I have some general idea of, one, how many solutions I have. So like if you think about my parabola, I could just have a line that touches the parabola. That means I'll only have one solution. If I have a line that cuts like that, I'm going to have two solutions. If I have a line that's like this and never touches my parabola, I'm never going to have any solutions. And that comes down to, again, the quadratic formula and that thing inside the square root. But we'll get to that later. So all I want to be able to do is try and draw these things. So let's try and draw them. I know that this, whoops, thinner please. I know that that is my gradient, and I know that that is my y-intercept. So I can quickly draw those on my graph. So y-intercept of -3, and then a gradient of 2 would kind of look like this perhaps. Yeah, and I can find what that x-intercept is. So that x-intercept would be if y was 0, and then I move this over, so then that's a 3, and then I divide by 2, so that's actually 3 on 2. So see how fast you can start doing these things? Okay, 3 on 2 is 1.5. Maybe for scale I'll put 1.5 in there. if you're not sure, if I'm doing that way too fast, then that's stuff we've done before. I don't want to spend ages on it. Okay, now I wanted to be able to draw this parabola. So again, there's a few ways of doing that. I can find my x-intercepts, but I can see from this thing that there's a couple of things I look at a parabola and I can quickly tell. The first thing is that I can't factorize it nicely because no two numbers times together to give 1 and then add to give -3. So I'm not going to be able to factorize it nicely. If I complete the square, I'm also going to have gross things. Like if I halve this and then square it, so that's 3 on 2 squared, so that's 9 on 4. That's gross too. So I don't really have to deal with that. Then I'd have to use a quadratic formula, and that's going to give me surds and stuff. So I don't really want to do that. So maybe I'll just find the axis of symmetry. So axis of symmetry, I think that's the nicest one. So I'm going to find out where the vertex is. And this tells me that it's concave up, so like that, because it's positive. Now the axis of symmetry is going to be x equals minus b on 2a, which is 3 on 2. Okay, so 3 on 2, that's 1.5. So it's actually got the same axis of symmetry as my x-intercept here. So the axis of symmetry is going to be like this. Okay, I don't really know where my vertex is, so what I can do is I can substitute the y value in. So then I've got 3 on 2 squared minus 3 outside 3 on 2 plus 1. That means my y value is, calculator, 3 on 2, whoops, 3 on 2 squared minus 3 times 9 on 2 plus 1. Minus 5 on 4, which is minus 1.25. Okay, so it's about minus 1.25. Let's call that there, minus 1.25. So the vertex is going to be there. So then my parabola is going to be like that and like that, which means this line can go on forever. Let's draw it so it goes on forever. Okay, let's suppose it. God damn this line. Okay, this parabola looks terrible. Alright, so I'm looking for a point here. And I'm looking for a point there. They're my goals. Okay, now let's do it algebraically. So the only reason I did that was so I have a general idea of where my solutions are. So let's verify whether those make sense. So algebraically, now I've got my two equations. They're y equals 2x minus 3 and y equals x squared minus 3x plus 1. Now I like to write them on top of each other like that, and then I name them. So I'm going to call this 1, I'm going to call that 2, and there's a bunch of different ways of doing this, but the easiest one is to just be like, okay, well if y equals all of this, and y equals all of that, then doesn't that just mean this equals that? So I hope that makes sense. So I'm going to make 1 equal 2. So 2x minus 3 equals x squared minus 3x plus 1. I'm going to move everything that away. So then it's 0 equals x squared minus 5x plus 4. Now hopefully this factorizes nicely. Minus 1 and minus 4, I'm thinking x minus 1, x minus 4. Okay, that means x equals, why I wrote it like that. That means x equals 1 and 4. Okay, so now I need to find my y values because these are points. I think it's really obvious which one's 1 and 4. So this one's going to be 4. This one's going to be 1 because like 1 and then 2, 3, 4. Anyway, okay, so when x, oh, God's sakes. So I like to write it like this. When x is 1, y is equal to, now you have a choice. You can put it into either one you like. So actually, let's narrate what we're doing. So I'm going to go x equals 1 into, and you can choose. I think the nicest one to substitute into is this one, obviously, because then this one's a lot bigger. So I'm going to put that into 1. So that's going to be y equals 2 times 1 plus 3. So then y equals 5. Okay, so when x is 1, y is 5. No, that's not right. That's a minus. I was going to say, do you want to know how I realized that that was wrong? because I was like 5. Okay, so that means this is 5. How the hell does that make sense? 5 would be up here. So I saw my mistake easily. I obviously didn't set that up. So can you see how drawing it just saved me, kind of? Because I definitely wouldn't have, I would have just left that. Anyway, okay, so this is -1. So that actually makes sense because that's down there. So that's that point. So the point, actually, let's leave that. Okay, so then I'm going to put x equals 4 into 1. Okay, so then that's y equals 2 times 4 minus 3. That means y equals 8 minus 3 is 5. Okay, so this one's 5. So that's up there. So you can see that makes sense. So across 4 and up 5, that looks like it makes sense. So then, okay, let me just conclude. So therefore, they intersect at 1 minus 1 and 4, 5. And you can see that a couple of things kind of arose from this. If you'd found that there was only one solution, then it might have been the fact that the line kind of just touched it, like I was saying before. If you got to this point and it wasn't solvable, so if you tried to use the quadratic formula on it and it didn't work, like if you ended up with a negative square root, then your line was probably underneath your parabola or something like that. So these are all the things you can think about when you are able to draw them quickly. And I know I wasn't really able to draw that heaps quickly, but with some of these other ones, you will be able to. Okay, so that's A. Let's do B. Let me draw a line across that so I can differentiate. Okay, B. What do we got? Should I do it geometrically and algebraically again? Yeah, we'll do that. So geo, that's an O. Geo and alg. Okay, so geometrically, what are our lines there? Y equals x plus 2. So y, what I got? Y equals x plus 2 and x squared plus y squared is 4. So I can't really write these on top of each other. Equals 4. Okay, so x plus 2 is just, that's x, and then I plus 2, so it's up there. Or another way of thinking about that is y-intercept of 2, gradient of 1. That's my first one. My second one's a circle with radius 2, so 2 squared. So I can just draw a circle. Now, have a think about this as well. Whereabouts is your circle going to like meet this line? And because this is 2 up, a good way to draw a circle is if it's got a radius of 2, just go ahead and be like, okay, 2 minus 2, that is actually 2, so that's something you could verify. But if I wanted to know my x-intercept, I'd make y equals 0, and then I move that over, and I know that that's x minus 2, so I know that it's going to cut at this point, so that there is minus 2. And so then I can draw my circle now. This is going to be a real month of mine. Oh, no, that's perfect-ish. Okay. Okay, and then from that, I can identify where my solutions are. My solutions are that point there and that point there. And you can see I actually already know what they are. Is that right? Yeah, right. I actually already know what they are. I don't really need to dive into any algebra. I know that that point is just literally based off the picture. 0 across 2 up. So that's 0, 2. And this one is minus 2, 0. So I actually know what they are. But you can imagine that if your line was like this, then it'd be a little bit harder, wouldn't it? So I actually know what these 2 points are, but let's go with the algebra. Let me get rid of that. Okay. So this, just write as a radius 2. Okay. Now, the second type of way of solving simultaneous equations is I'm going to call this 1 and call that 2. Instead of putting them equal to each other, because I don't have y as the subject in either of them. You could do that, but the problem is you can end up with a plus minus, and that's kind of weird. So the easier thing to do here is just go ahead and put 1, substitute 1 into 2. So if y equals all this, and I've got a y in here, I'm just going to put this in here. So then I've got, so this implies x squared plus, and then inside there, x plus 2 squared equals 4. Then you just got to expand everything. So I'm going to do this all in one step. X squared plus 4x plus 4 equals 4. Okay, so that's now 2x squared plus 4x. I'll move that 4. That's going to be plus 0 now. Equals 0. So those 4s are going to cancel. Bye. Okay, now I'll divide everything by 2. So x squared plus 2x equals 0. Now I'll factorize x outside of x plus 2. Okay, so that means x equals 0 or x equals minus 2. And I can see that I already have those solutions, 0 and minus 2. So that's nice. So then I'll go ahead and go, okay, I'm running out of room. It's not good. Go there. So then, okay, so x equals 0. I'll put that in 1. A more wobbly. Put that in 1. So then y equals 0 plus 2, which equals 2. And then I'll put x equals minus 2 in 1. So then that's y equals minus 2 plus 2, and that equals 0. So therefore, they intersect at 0, 2, 0, 2, and minus 2, 0. Minus 2, 0. And I already have those. Minus 2, 0, 0, 2. Okay, so again, it's kind of nice to be able to verify your solutions. Damn it, this video is long. Okay, last one. Geo, alg. What are the questions I have in here? It's y, try and do this faster. Y equals, I've lost it, I just said I was going to do it faster, x plus 5, and then y equals 6 on x. So this comes to an identification of what these graphs actually are. So y equals x plus 5, that's obviously a line, and looks like that. And that y-intercept is 5. And then I've got this thing over here, so x, 6 on x. So that's an exponential. Just kidding, it's a hyperbola. And a hyperbola looks like one of those things where it's like this or like this, and because they're both positive, it is in these quadrants. If that was a negative, it'd be over here. So I'm just going to quickly draw that and that. Why did it break like that? Okay, so you can see there's two solutions again. So the first one's there, and the second one's here. Okay, so then I have a general idea where they are. So now I'll go ahead with the algebra. And again, because y equals this and y equals that, that means these two things equal each other. So call this 1, call that 2. So I'm going to make 1 equal 2. And this is how I want you to lay it out. Don't skip steps. This is essentially a proof. So then I've got x plus 5 equals 6 on x. So then I'll times the x up. So then that's x squared plus 5x. Actually, I'll put that in brackets. So x outside of x plus 5 equals 6. So then that's x squared plus 5x equals 6. And then x squared plus 5x minus 6 equals 0. Then I can factorize that as x. I'm thinking 6 and 1. 6 minus 1 equals 0. Let me check that. 6 minus 1 is 5. 6 times minus 1 is minus 6. Good. That means x equals minus 6 or 1. Okay, so that means this is 1. And that must be the minus 6 one. Yeah, so just checking whether these make sense. So then x equals minus 6. We'll put that into, it's probably easier to put that in, no, it doesn't really matter, does it? Let's just put it into 1. So then y equals minus 6 plus 5. You don't know what I'm doing here, I'm just substituting minus, so x for this. So then that's minus 1. So therefore intersect at, so the first one is minus 6 minus 1. And then the second one, so I'm going to put x equals, what's the other point? 1. Put that in 1. So then y equals 1 plus 5. Means y equals 6. So the other point is 1, 6. So that's the point 1, 6. And that's the point minus 6 minus 1. Easy. Maybe not easy, but this is kind of as hard as it gets, actually. Because these are simultaneous equations, but they're non-linear. So non-linear in that I'm looking at things that aren't just straight lines, particularly like the first one, how it's a parabola and a line. These are non-linear simultaneous equations, and you can actually solve this. The people that were doing it using those matrices, you can actually do it using that. So that's kind of interesting. The the only way to do it is either by the equals or by putting things into other things. So yeah, I know this has been a little bit of a mess, but I hope that it kind of makes sense, and it's definitely an advanced thing. It's not something you'll do in standard at all. So if it's not making too much sense, at the end of the day, all I really want you to be able to do is draw these things and locate where the solutions are. Once you do that, the algebra hopefully should come secondhand, but I just want you to be able to identify where your solutions are, and you can check them using algebra, or the opposite. Do your algebra and check your solutions by drawing the two things. That's really all I care about. I don't want this to go for any longer, but that is the topic. So that's graphing. That's it.